So in this video, I will say a few more words about the support vector machines. So you must watch all the videos where I talked about support vector machines. I think so far I recorded 3 videos. You must watch all the 3. If not, you will have no clue that what I'm going to say now in this video. Yeah. So what we learned so far is obviously how the algorithm of a support vector machine works, and then I also explained how what it can do, and we also learned something about the hyperplane and support vectors. Yeah? So we have 3 linear equations, isn't it? Yeah? So that's what we derived, or we proved that these 3 equations are really important in the language of support vector machines. So the one linear equation that corresponds to hyperplane, and another equation that corresponds to one of the support vector, and another equation that corresponds to the Euler linear equation that corresponds to another support vector. Yeah? And typically the distance between these two, one of the support vector and the other support vector, that defines the so-called margin. Yeah? So probably in this video itself I will do some derivations and show how to calculate the margin, so-called margin, mathematically. Yeah? So you have to remember what this 3 equation means, so only then you will understand. But before that, what I'm going to show you is I did some calculations using Microsoft Excel. All I did is I tried to solve the same problem which we solved using pen and paper earlier, and I want to show you how the data looks like if you really project it on the so-called the best vector. So these are the experimental data, isn't it? So this is what we solved using pen and paper. So we have 4 samples that corresponds to circle, and then we have 4 samples that corresponds to rectangles, and then we have its length, and then its width, and then we wanted to use support vector machine. So to classify these 2 categories. So you have to identify which one belongs to circle and which one belongs to rectangle, and obviously we know how to get the hyperplane. So hyperplane is something, this blue line, and this blue line is nothing but the vector w. So this is the vector w, shown here as a dotted purple line. So and then we try to project the data in this purple line, and then we make sure, so if you project all the x, which is x1 and x2, so x1 is length and x2 is width, if you project it using the formula wtx, then after projection your data will look something like here. So and then this particular point, follow the cursor, this particular point is something we labeled it as a p max, and this particular point is something that we labeled it as p minimum in the second class, the second category. And we have to identify the best direction of the vector w, where this distance between p max and the p minimum that belongs to the other category should be maximum. So this is what we try to do using the support vector machine, and the entire game begins with identifying the best direction, which is this vector. Follow the cursor in the video. And then from there we can multiply, we can take the transpose of this vector. So what this vector will look like. So this vector will be, say, 1 minus 1, or it can be 1 minus 1 1. So both point towards the same direction, isn't it? Or it can be even 2 and minus 2. So all this number points towards the same direction. So the number doesn't matter, but what matters is the direction of the vector. So once you know the correct direction of the vector, then we can project the our data x1 and x2 onto the corresponding vector, where we think that's the best direction, and that ensures the separation between p max and the p minimum is maximum. So this is what I did. I just wanted to show the graph in this video, nothing else. And that's our vector 1 comma minus 1. This vector can be 2 comma minus 2. Nothing, doesn't matter what the number is. What matters is 2 comma minus 2 or 3 comma minus 3, all points towards the same direction. And then I also tried to, for fun, I just made another vector that looks like here. So 1 comma 0. So 1 is what? 1 is somewhere here on the x-axis. 0 means 0 on the y-axis, which means that vector should be this one, yeah, which is the x-axis. And if you try to project the data point onto these vectors, then you may get something like this. I can plot it. So this is the data projected onto the vector 0, 1, 0, which is you just project all the data points on the x-axis, and then if you plot it, you will see one thing you can immediately notice is, so the distance between the p max, just follow the cursor, and the p minimum in the second category is not great, isn't it? It's not as large as when you project the same data onto a different vector. Yeah? So this is what I mean. So you have to find the vector or the right direction where you project your data, and in that direction you have to observe that the p max, distance between p max and the p minimum, or the distance between the support vectors is maximum. Yeah, so the game of support vector machine is to maximize this distance between these two support vectors. So which means you need to calculate. So if you want to write a program where you can maximize the distance, so you have to identify, or you have to come up with an expression, that something that we can call it as the distance between these two vectors. Yeah, so I will try to derive such an equation. Yeah, so which we can use it when we are going to write the code using MATLAB. Yeah, so that's the take home message. So you have to find the right direction. If you have a different, if your vector is not pointing towards the right direction, then obviously this distance will be smaller than the optimal distance. Yeah, so that's the message. I will also show you now, after this I will show you now how to calculate the distance between these two vectors, or the so-called margin. So what I'm talking about is, I'm going to show. So let's say you have something variable 1, variable 2, and then you have some data points here, and then let's say you manage to get the hyperplane on the support vectors. I will show you how to calculate the distance, or we will derive a mathematical expression that allows you to calculate the distance between the support vectors. So in the game of SVM, all we try to do is we will try to maximize the distance, between the support vectors. Yeah, so this is something we will see now. So let's try to calculate, or do some mathematical derivation that allows you to calculate the distance between these two support vectors, yeah, which is something we will call it as margin. So how to do that? So for the sake of convenience, what I'm going to do is I'm going to, let's say we have a graph like that. So variable 1 on one side, variable 2 on the other side, or we can put x1, x2, some convenience, and then we have something on this side, something on the, some samples on the, set of samples on the other side, and there is a hyperplane that looks like that. And we know the equation of hyperplane is w2x plus b equal to 0, and then let's say we have one support vector and another support vector on the other side, and for the moment let's say one side w2x plus b equal to plus 1, and another side, let's say the equation of support vector machine is w2x plus b equal to minus 1. So we have three linear equations here, and we have to calculate the distance between these two margins. So one way to do is, so let's say we calculate the distance starting from origin 0, 0, which is this point, and let's say we calculate the distance between origin to here, something like here. Let's say let's call this distance a, and then we also calculate the distance between 0 to the second support vector, and let's call that distance from here to here as b. So to get the distance between these two support vectors, all we need is to subtract this distance minus this distance, yeah, which means a b minus a. So that should give mathematically at least the distance between the support vectors, or the so-called margin in the language of SVM. So how to do that? Yeah, so let's say this point 0 comma 0, let's call this as point x0. So we already learned, isn't it? So this is one vector that has a meaning, and that meaning is this vector is placed at the origin, which means x1 is equal to 0, x2 is equal to 0. And let's try to calculate the distance from here to this vector. Let's say wtx plus b equal to minus 1, and we try to calculate the distance from the origin 0 comma 0. So we are trying to calculate the distance between this support vector and the point x0. So how do you get that? So the distance between these two points is, we just take, so okay, first let's write this equation in the linear format. W to x plus b plus 1 equal to 0. So we're trying to calculate the distance between x0 and w to x plus b equal to plus 1 is equal to 0. So to do that, the distance between let's say a is equal to the mode of wt x0 plus b plus 1, that's divided by the norm of w. So that's the formula to calculate the distance between this point and the support vector. Yeah? Support vector given by the equation w to x plus b plus 1. Yeah? So this equation was proposed by Euclidean. He is called the father of geometry. So we don't have to go into the history of who is the father of geometry. Just to learn the formula. What's the formula it is? Yeah. And since x0 is 0 comma 0, so which means this whole term will become 0, isn't it? Yeah. So which means a is equal to just the mode of b plus 1 divided by the norm of omega. Omega is nothing but your vector which is pointing towards the best direction, where the distance between p max and p minimum is maximum. So similarly, you can calculate the distance between 0 comma 0 and the other vector w to x plus b plus a, which is equal to 1. Yeah. So let's write that the equation for that vector. So w to x plus b minus 1 is equal to 0, and we try to calculate the distance between this vector and x0, which is 0 comma 0. So that distance we are going to label it as b, right, which is the mode of w to x0 plus b minus 1 divided by the norm of vector omega. So again x0 is 0 comma 0, isn't it? Yeah. So this whole term becomes 0, so which means b will be mode of b minus 1, sorry, norm of mode of b minus 1, that's correct, divided by the norm of vector w. So now what you need to do? So now we have to do the distance between these two vectors, isn't it? Yeah. Sorry, the two support vectors. So how to do that? So just subtract b minus a. That should give the margin. Let's say, so to calculate margin, yeah, subtract b minus a. So this is very easy to do. So which is b minus a is equal to b plus 1, sorry, b minus 1 plus minus of b minus 1 divided by the norm of w, isn't it? Yeah. So what is this? Something is not correct. So this is b plus b minus 1 minus into 1, this one become plus. So 1 1 get something is not correct. Let's do this again. So this is equal to, say, let's rewrite b minus 1 divided by the norm of omega w minus b plus 1 divided by the norm of w. So if you subtract it, so that will be b minus 1 minus b minus 1 divided by the norm of vector w. So if you want, you can put an arrow just to say that this is a vector, but for the moment let's put w. So this means, which is equal to b gets cancelled, so it's minus 2 divided by the norm of w, which is your vector. So since you take the mode, this will be just 2 divided by the mode, isn't it? Yes, so which is 2 divided by the norm of the vector w. So this is what we try to calculate. So this is nothing but the something we can call it as the margin, or the distance between the two support vectors, 2 divided by the norm of vector w. Yeah, at some stage I may ask you to calculate these values. So I may give the equations, and then I will ask you to calculate the distance between the support vectors and the origin, which is 0 comma 0. So we're almost there, and now we have to calculate what we have to calculate. So not calculate, because now we are not doing any computation, but typically if you see that if you want to if you go back to this equation, so typically if you want to increase the margin, so increase the distance between the two support vectors, then all you need is to find, so you can identify the best direction just by increasing the margin, or you can minimize this one, which is your vector, isn't it? Yeah, so which means that is another way. So if you minimize the norm of vector, then you are obviously maximizing the margin. So that's one of the parameter that we will tune when we are going to deal with support vector machine. So that's one way to identify the best direction where the separation between the p max and the p minimum is maximum. So that's that should be enough for the moment. And something I wanted to highlight is, so this in the first video I said I will explain what is this SVM, whether it's I said it's a machine learning algorithm, but what type of algorithm is this? So this is something we can classify this algorithm as a supervised machine learning algorithm. So what do we mean by that? So imagine that you have some data, something one here, another data somewhere here. You have a lot of data, let's say these are data driven models, and then somehow we use this data to identify the hyperplane based on the best vector w, where that ensures the separation between p max and p minimum is maximum. And then from there we get our support vectors, based on the equations that we learned so far. And then once this decision boundary is fixed, so once the decision boundary is fixed, then we think, so how this machine learning algorithm works. So the algorithm, we know the algorithm is so and so, we already know what is a hyperplane, what is a support vector, what could be the distance between the support vector, and how do we get the hyperplane which is perpendicular to the vector, which is where that ensures the distance between these 2 points are maximum. And this is something we learned so far, isn't it? Yeah. So whenever I say a machine learning toolbox, or a supervised learning means we will build using computer something called like a box. That box contains SVM algorithm. So inside this box we will feed, just say x is nothing but x1 comma x2, and then we will find the hyperplanes, the best hyperplane, and then the support vector that corresponds to the hyperplane for the given data. Yeah, and then once the decision boundary is fixed, once the hyperplane is fixed and the margin is fixed, then we use this box. We call this box as prepared. And now what we do, we will give some new data, new x values, and then we will ask this box based on this fixed boundary and tell whether this belongs to category 1, which lies on the right side of the hyperplane, or does it belongs to category 2, which usually lies on the left side of the hyperplanes. And since we need some data to identify the hyperplane and its direction and the vector as well, omega, this is called as a supervised learning algorithm. So we have to give the data and we have to clearly identify the data that belongs to the left side of the hyperplane belongs to category 1, and the data that belongs to the right side of the hyperplane belongs to category 2, and the hyperplane itself comes from the given data. Yeah, so we have to use these data in order to get the hyperplane. So that's how the supervised learning algorithm works. So you need really a lot of data to prepare your toolbox where we will plug in the support vector machines. Yeah, so for the sake of convenience, as we just have pen and paper, we used a small data. Yeah, small data is something. So typically data dimension will be rows multiplied by columns. So we have we used eight rows and 2 columns. Yeah, so our data strength is 8 by 2. But obviously, if you have really large data sets, say like 10,000 rows multiplied by 2 columns, or even if you have more columns, still SVM will work. So if you have even for a big data, SVM works really good, provided there exists a gap. Yeah, after projecting it in the best possible direction. If this gap doesn't exist, if you remember, I said to you this somewhere I mentioned. So P max, yeah, this should be less than P minimum. So if this condition never exists, then we cannot use support vector machines. Yeah? But if this condition holds true, then obviously then we can use this type of algorithm. Yeah? So, and also for the sake of convenience, I know this module is something related to smart energy management and systems, but to learn the so-called algorithm or the mathematics of it, it is better to use very simple numbers. Yeah? For example, we used how the circle, how the rectangle looks like, and then we used we explained the concept of how what are the measurable quantities. Yeah? We call it as variable 1, variable 2, and then we try to plot it on a simple plot, and then we try to learn the whole algorithm. So once you know the algorithm, obviously you can use it for any problems, chemical engineering problems, or problem which is relevant to this module, or even to predict anything where you think 2 things changes, and you can clearly classify one system from the other system. Yeah, so the main thing is you should have the knowledge, and then how do you apply it for your problem, that's up to you. Yeah, so I'm going to end the talking about support vector machines, and probably in the next video I will introduce you to one more algorithm, something called as a principal component analysis, shortly PCA. Very simple algorithm. It has only 7 steps, and we will execute the 7 steps in a particular fashion. And this one belongs to unsupervised machine learning algorithm. Yeah, so I will explain later why this is called unsupervised. Yeah, and this algorithm is supervised because we already labeled our data. Something belongs to circle, something belongs to rectangle. So we need that information as a known priori in order to implement this type of algorithm. So that's why it's called as a supervised learning algorithm. Yeah, so thanks for listening.